Welcome! In this session, we're diving into problem number 654, titled Maximum Binary Tree. We'll explore the problem, break it down step by step, and analyze different approaches to find an efficient solution. Let's get started. In this problem, the goal is to construct a maximum binary tree using a given array of distinct integers, nums. The construction process is defined by three key rules. First, the root of the tree is the maximum value in the entire array. Second, the left subtree is constructed recursively using the elements that are to the left of this maximum value in the array. Third, the right subtree is constructed recursively using the elements that are to the right of the maximum value. The output of the function will be the root node of this binary tree. Each node in the tree will have three attributes: val, which is the value of the node, and left and right, which are references to the left and right child nodes, respectively, or null if the child does not exist. Now let's look at an example to understand this better. Suppose the input array is nums equals 3, 2, 1, 6, 0, 5. The output is a binary tree that has the value 6 as its root, because 6 is the maximum value in the array. The left subtree is built from the elements 3, 2, 1, while the right subtree is built from the elements 0, 5. The resulting tree has 3 as the left child of 6, and 5 as the right child of 6. Continuing further, 3 has a right child 2, which in turn has a right child 1. On the right subtree, 5 has a left child 0. This structure is shown in the diagram. To break this example down further, here's how the tree is constructed step by step. The maximum value in the array nums is 6, so it becomes the root of the tree. The elements to the left of 6, which are 3, 2, 1, are used to build the left subtree. In this subarray, 3 is the maximum, so it becomes the left child of 6. The elements to the right of 3, 2, 1, are used to build its right subtree. Here, 2 is the maximum, so it becomes the right child of 3. Finally, the remaining element, 1, becomes the right child of 2. On the right side of the root, the subarray 0, 5 is used to build the right subtree. The maximum value 5 becomes the right child of 6, and the remaining element 0 becomes the left child of 5. This recursive process ensures that the tree is constructed according to the rules. Let's consider another example with the array nums equals 1, 2, 3, 4. Here, the maximum value is 4, so it becomes the root of the tree. The elements to the left of 4, 1, 2, 3, are used to build the left subtree. In this subarray, 3 is the maximum, so it becomes the left child of 4. The elements to the left of 3, 1, 2, are used to build its left subtree. Here, 2 is the maximum, so it becomes the left child of 3. Finally, the remaining element, 1, becomes the left child of 2. There are no elements to the right of 4, so the right subtree is null. This results in a left-skewed tree where all nodes only have left children. Now let's examine a third example with the array nums equals 7, 8, 9, 10. In this case, 10 is the maximum value, so it becomes the root of the tree. The elements to the left of 10, 7, 8, 9 are used to build the left subtree. In this subarray, 9 is the maximum, so it becomes the left child of 10. The elements to the left of 9, 7, 8 are used to build its left subtree. Here, 8 is the maximum, so it becomes the left child of 9. Finally, the remaining element, 7, becomes the left child of 8. As there are no elements to the right of 10, the right subtree is null. This produces another left-skewed tree. Let's discuss a few edge cases. If the array contains a single element, for example nums equals x, the tree will consist of a single node with the value x and no children. For an array in strictly increasing order, like nums equals 1, 2, 3, the tree will be skewed to the left, with each node having only a left child. Conversely, for an array in strictly decreasing order, such as nums equals 3, 2, 1, the tree will be skewed to the right, with each node having only a right child. These edge cases highlight how the structure of the tree depends on the arrangement of values in the input array. To solve the maximum binary tree problem, the brute force approach is the most straightforward method to consider first. The intuition here is simple: we follow the problem's rules directly. Start by finding the maximum element in the array, which becomes the root of the tree. Then, divide the array into two parts: elements to the left of the maximum and elements to the right. Recursively apply the same process to construct the left and right subtrees. However, this approach has some evident drawbacks. The key issue is that finding the maximum value in a subarray requires scanning it, which takes n time each time. Since this process is repeated for each recursive step, the overall time complexity can grow to n squared in the worst case. This happens when the input array is sorted in ascending or descending order, leading to highly unbalanced trees. Additionally, this approach creates new subarrays during each recursive call, which increases memory usage. While simple to implement, it is inefficient for larger input arrays due to these performance limitations. To overcome the inefficiencies of the brute force method, we can use an optimized approach based on a monotonic decreasing stack. This strategy eliminates redundant maximum searches and constructs the tree more efficiently. The process begins by traversing the array from left to right while maintaining a stack where the elements are in decreasing order. For each element, if it is greater than the top of the stack, it becomes the parent of the smaller elements being popped from the stack. The last popped element becomes the left child of the current element, while the current element becomes the right child of the last element remaining in the stack. Finally, the current element is pushed onto the stack. This stack-based approach ensures that each element is processed only once, giving it an overall time complexity of n. Moreover, it avoids creating new subarrays during the process, resulting in a space complexity of n, which is primarily due to the stack. While this method requires a deeper understanding of how the stack manages the parent-child relationships in the tree, it is significantly faster and more memory efficient, especially for larger input arrays. The monotonic stack approach has been chosen as the preferred strategy because it directly addresses the inefficiencies of the brute force method. By reducing the time complexity from n squared to n, it avoids the costly repeated scans of subarrays. Additionally, it eliminates the need for slicing the array during recursive calls, which makes it more memory efficient. One of the key insights here is that the parent-child relationships in the tree can be managed dynamically during a single traversal of the array. This allows us to construct the tree in a streamlined manner while maintaining efficiency. Although the monotonic stack approach may initially seem less intuitive than the brute force method, its significant performance improvements make it the better choice. The trade-offs are minimal. While both methods have linear space complexity, the stack avoids the additional memory overhead caused by subarray creation in the brute force approach. In conclusion, the monotonic stack approach is the optimal solution for constructing the maximum binary tree. With its linear time complexity and memory efficiency, it is well suited for handling large input arrays effectively. The monotonic stack not only simplifies the construction process but also systematically manages the parent-child relationships in the tree with minimal overhead. This makes it a robust and scalable solution, balancing performance and clarity while addressing the drawbacks of the brute force approach. Ultimately, it is the best strategy to solve this problem efficiently and systematically. In this problem, we aim to construct a binary tree from an array using a specific set of rules. The key idea is that the maximum value in the array becomes the root of the tree. Then, we split the array into two parts. The elements to the left of the maximum form the left subtree, and the elements to the right form the right subtree. This process is applied recursively to build the entire tree. To get started, we define our base cases. If the array is empty, there is no tree to construct, so we return none. If the array contains only one element, we simply create a tree node with that value and return it, as no further recursion is needed. Once the base cases are established, the next step is to find the maximum element in the array. Identifying this maximum value is crucial because it determines the root of the tree at the current level of recursion. After locating the maximum, we can split the array into a left subarray, containing elements before the maximum, and a right subarray, containing elements after the maximum. Using this maximum value, we create a new tree node, which serves as the root node for this level of recursion. Now that the root node is created, we proceed to construct its subtrees. The left subtree is built by applying the same algorithm recursively to the left subarray, and the right subtree is constructed by doing the same with the right subarray. Once both subtrees are constructed, they are attached as the left and right children of the current root node. This approach ensures that the tree adheres to the problem's rules at every level. The recursion continues, splitting the array into smaller and smaller parts, until we reach the base case, either an empty array or an array with a single element. At this point, we combine all the results and return the constructed tree node as the root for the current recursive step. This method leverages a divide and conquer strategy, effectively breaking the problem into smaller, manageable pieces. The maximum value at each step guarantees that the tree is built optimally according to the rules. The depth of recursion depends on the structure of the array. For example, a sorted array results in maximum depth of O, n, while a more balanced array leads to a depth closer to O log n. To implement this approach, we primarily rely on two data structures. First, the array itself is used to identify the subarrays for constructing the left and right subtrees. Second, we use binary tree nodes to store the tree structure. Each node holds a value, a reference to its left child, and a reference to its right child. Analyzing the algorithm's complexity, the time complexity is driven by the process of finding the maximum element in the array, which takes O, n, and the recursive calls on subarrays. In the worst case, such as with a sorted array, the algorithm's time complexity becomes O, n squared. However, in a more balanced case, the time complexity improves to O, n log n. Space complexity, on the other hand, is determined by the recursive call stack, which can go as deep as the number of elements in the array, leading to O, n space complexity. As an example, consider the array 3, 2, 1, 6, 0, 5. The maximum value is 6, so it becomes the root of the tree. The array is then split into 3, 2, 1 for the left subtree and 0, 5 for the right subtree. To construct the left subtree, we find the maximum value in 3, 2, 1, which is 3, and create a node with this value. This splits the array further into an empty left subarray and 2, 1 as the right subarray. Recursion continues until all subarrays are processed. For the right subtree, we start with the array 0, 5. The maximum value is 5, so we create a node with this value. This splits the array into 0 for the left subtree and an empty array for the right subtree. The left subtree is constructed from 0, which directly results in a node with value 0 since it is a single element array. The right subtree, being an empty array, results in none. As the recursive calls return, the subtrees are combined to form the complete tree. When all recursive steps are completed, the final tree structure is as follows. The root node is 6, with 3 as its left child and 5 as its right child. Node 3 has no left child but has 2 as its right child. Continuing further, node 2 has no left child and 1 as its right child. On the right subtree, node 5 has 0 as its left child and no right child. This structure ensures that the tree adheres to the problem's rules, with the maximum element always serving as the root at each level. This code solves the LeetCode problem number 654, maximum binary tree, by constructing a binary tree where the root is the maximum value in the input list, and the left and right subtrees are recursively constructed from the subarrays to the left and right of the maximum value, respectively. We start by defining the treeNode class, which represents each node in the binary tree. Each node has a value, val, and pointers to its left and right child nodes, left and right. The construct maximum binary tree function is implemented within the solution class. This function takes the input list, nums, and constructs the maximum binary tree. The first step is the base case. If the input list is empty, the function returns none, indicating there is no tree to construct. Next, the maximum value in the list is identified using Python's max function, and its index is determined with the index method. This maximum value becomes the root of the current subtree. A new tree node is created with this maximum value. The left subtree is then recursively built by calling construct maximum binary tree on the subarray containing all elements to the left of the maximum value. Similarly, the right subtree is recursively built using the subarray of elements to the right of the maximum value. Finally, the function returns the root node of the constructed tree. The recursion ensures that the entire binary tree is built correctly according to the problem's requirements. This approach ensures that the tree is constructed in O, n squared time in the worst case, when the input list is sorted in descending or ascending order, as finding the maximum takes O, n time for each recursive call. However, the implementation is straightforward and effectively solves the problem within the constraints. Here, we start by defining the basic structure of a tree node class, which represents each node in our binary tree. Each node has a value, a reference to its left child, and a reference to its right child. In the constructor, we initialize the node's value and set both child references to null. Then, we move on to the solution class, where we implement the construct maximum binary tree method. This method takes an array of integers as input and is responsible for constructing the maximum binary tree. First, we handle the base case. If the input array is empty, we simply return null, as there are no elements to construct a tree. Next, we search for the maximum value in the array. To do this, we initialize a variable max index to 0, assuming the first element is the largest initially. We then iterate through the array, updating max index whenever we find a larger value. After determining the index of the maximum value, we create a new tree node using that value. This node becomes the root of the current subtree. Now, to construct the left subtree, we recursively call construct maximum binary tree with the portion of the array that lies to the left of the maximum value. Similarly, for the right subtree, we use the portion of the array to the right of the maximum value. The arrays.copyOfRange method helps us extract these subarrays efficiently. By recursively repeating this process, the tree is built layer by layer, with the largest value in each segment becoming the root of its respective subtree. Finally, we return the root node, which represents the fully constructed maximum binary tree. To solve the maximum binary tree problem, we start with the given input array nums equals 3, 2, 1, 6, 0, 5. First, we check if the array is empty. Since it is not, we proceed to find the maximum value, which is 6, located at index 3. We create a tree node with the value 6, and this becomes the root of our tree. Next, we divide the array into two parts, elements to the left of 6 and elements to the right of 6. For the left subtree, we use the subarray 3, 2, 1. Here, the maximum value is 3 at index 0. A tree node with value 3 is created. Since there are no elements to the left of 3, the left subtree is none. For the right subtree, we use 2, 1. The maximum value in this subarray is 2 at index 0. So we create a tree node with value 2. Again, the left subtree is none, and for the right subtree, we use 1, where the maximum value is 1, creating a tree node with value 1. Both left and right subtrees of this node are none as there are no more elements to process. Now, returning to the right subtree of the root, we focus on the subarray 0, 5. The maximum value here is 5, located at index 1. A tree node with value 5 is created. For the left subtree, we use the subarray 0, where the maximum value is 0. A tree node with value 0 is created, and since there are no elements left to process, both the left and right subtrees of this node are none. Meanwhile, the right subtree of the node with value 5 is also none because there are no elements to the right of 5. This completes the construction of the tree for the input nums equals 3, 2, 1, 6, 0, 5, with the root node being 6, and the subtree structured as determined. Let's consider another example with nums equals 1. Here, the maximum value is 1, located at index 0. We create a tree node with value 1. Since there are no elements to the left or right, both the left and right subtrees are none. This results in a single node tree. Now, for the input nums equals 5, 4, 3, 2, 1, the maximum value is 5 at index 0. A tree node with value 5 is created. For the right subtree, we use the subarray 4, 3, 2, 1. The maximum value here is 4, so a tree node with value 4 is created. This process is repeated 4, 3, 2, 1, 2, 1, and finally 1, creating nodes with values 3, 2, and 1. Since all maximum values are always at the start of their respective subarrays, the tree becomes right-skewed, with each node linked to the next smaller value as its right child. To summarize the outputs, for the first example, the constructed tree has 6 as the root, with the left subtree containing nodes 3, 2, and 1, and the right subtree containing 5 with 0 as its left child. For the second example, the tree is simply a single node 1. For the third example, the tree is entirely right-skewed, starting with 5 as the root, followed by nodes 4, 3, 2, and 1 as consecutive right children. These examples illustrate how the maximum binary tree is constructed from the given input arrays. The time complexity of the construct maximum binary tree function stems from three main operations. First, finding the maximum element in the array using the max function takes O(n) time since it needs to scan the entire list. Next, the slicing operations nums max_index and nums max_index +1 create new subarrays, and their time complexity depends on the size of the subarrays, which can vary. Finally, the function makes recursive calls to build the tree on the left and right subarrays, with the size of these subarrays determined by the position of the maximum element. In the worst-case scenario, the input array is sorted in either decreasing or increasing order. This means the maximum element is always at one end, and the recursive calls process subarrays of size n1, n2, and so on. The recurrence relation here is T(n) equals O(n) plus T(n1), which expands to T(n) equals O(n) plus O(n1) plus O(n2) plus O(1). This leads to a worst-case time complexity that grows quadratically. This quadratic growth simplifies to a time complexity of O(n) squared in the worst case. On the other hand, in the best-case scenario, the array is structured such that the maximum element is always located near the middle. This results in the array being divided roughly in half at each step. The recurrence relation for this scenario is T(n) equals O(n) plus 2 * T(n/2). Using the master theorem for divide and conquer algorithms, this simplifies to T(n) equals O(n* log n). Moving on to space complexity, we need to consider both auxiliary space and recursion stack space. Auxiliary space arises from the slicing operations, where new subarrays are created. In the worst case, these operations require space proportional to the size of the input, or O(n). Additionally, recursion stack space depends on the depth of the recursion tree. In the worst-case scenario, the tree is skewed, meaning the recursion depth is O(n). In the best-case scenario, the tree is balanced, and the recursion depth is O log n. Combining these factors, the total space complexity in the worst case is O(n), due to both recursion stack and slicing operations. In the best case, the space complexity remains O(n), dominated by the space required for slicing. Comparing this approach to a brute force method, where all possible subarrays are explicitly iterated over, the divide and conquer strategy is far more efficient. A brute force approach could lead to exponential time complexity, while this implementation keeps the time complexity manageable. Finally, one optimized version of this algorithm could involve passing pointers or indices instead of creating new subarrays. This would eliminate the auxiliary space cost of slicing, reducing the space complexity to O(n), and slightly improving runtime efficiency. To mathematically justify these big O complexities, we analyze the recurrence relations and their expansions. The slicing operation and the process of finding the maximum element dominate the time complexity, resulting in O(n) squared, in the worst case, and O(n* log n, in the best case. These calculations confirm that the algorithm's performance is directly tied to the way the array is structured and how the maximum element divides the problem into subproblems. Understanding these mathematical properties ensures clarity in both analyzing and optimizing the algorithm. When solving the maximum binary tree problem, there are a few common mistakes that can trip you up. First, it's crucial to account for edge cases, such as when the input array is empty or contains only a single element. These scenarios can often lead to index out-of-bound errors or unexpected outputs if not handled explicitly in your code. Next, inefficiencies in recursion or redundant calculations can significantly slow down your solution. If your approach involves recursion, you should ensure that you're not repeatedly solving the same subproblems. Techniques like memoization or even shifting to an iterative approach can help optimize performance. Another potential pitfall is overlooking the problem constraints. For instance, if the input size can be as large as 10 to the power of 5, a brute force solution with O(n) squared complexity will almost certainly time out. Always analyze the constraints and choose an approach that scales well with the input size. Finally, be cautious about directly modifying the input array. Operations like sorting or partitioning can introduce unintended side effects, so it's often better to work with a copy of the array or carefully structure your modifications to avoid impacting other parts of your logic. Another mistake to watch out for is assuming the input is always valid. Test cases might include unexpected inputs, such as negative values or duplicates, which could cause problems if your solution doesn't handle these scenarios gracefully. Either ensure your logic is robust against such inputs or clearly document any assumptions you make about the input's validity. Now, let's talk about some interview-specific insights. Recognizing patterns in the input is a key skill. For example, identifying properties like maximum or minimum values, or noticing that the input is sorted, can simplify your approach. If the problem involves breaking the array into smaller parts, such as with binary search or recursion, focus on efficient divide-and-conquer strategies to minimize redundant work. Additionally, clear communication is critical during interviews. When you're analyzing edge cases or deciding on an approach, explain your thought process out loud. This not only demonstrates your problem-solving skills but also helps the interviewer follow your reasoning. Finally, testing your solution is a must. Walk through your code with a few examples, including edge cases, to confirm correctness and catch any potential bugs. To deepen your understanding of the maximum binary tree problem, it's helpful to explore related problems. Examples include constructing a binary tree from pre-order and innerorder traversals, LeetCode 105, or from innerorder and post-order traversals, LeetCode 106. Other problems, like converting a sorted array to a binary search tree, LeetCode 108, share similar concepts and can reinforce your skills in tree construction. When considering alternative approaches, divide and conquer is a common and often optimal strategy for this problem. By recursively splitting the array based on properties like maximum values, you can build the tree efficiently. However, keep in mind the trade-off: while this approach is elegant, it can be memory-intensive due to the recursion stack. Alternatively, you can use an iterative approach with a stack or queue to simulate recursion. This avoids stack overflow issues, especially for large inputs, but it can be more challenging to implement correctly. For problems involving multiple queries, pre-processing the input, such as building a segment tree, can drastically improve the time complexity of subsequent operations. Of course, this comes with a higher upfront cost, so it's important to balance pre-processing time against the expected number of queries. That wraps up our discussion on the maximum binary tree problem. We reviewed the problem, explored a brute force approach, and touched on optimization strategies. Remember, mastering recursion and divide and conquer techniques is key for problems like this. Thanks for watching, and don't forget to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!